Welcome you all to IIT PAL. In this problem solving session, we will cover concept based problems of aldehydes, ketones and carboxylic acids. As all of you know well, aldehydes, ketones and carboxylic acids are important class of compounds. They find broad utilities in synthetic chemistry. We will try to cover most of the problems to the preparation and reactions of aldehydes and ketones and carboxylic acids. So let us begin with reaction of compound A with ozone followed by zinc and water produces X and Y. Both X and Y show positive haloform test, while only X shows positive tolerance and Felling's test. Identify A, X and Y. From this molecular formula, you can understand it is an alkene. Since it fits with CN, H2N general formula. Now let us look at the properties of the products. Both X and Y show positive haloform test. That means both compounds have methyl group which is bonded with a carbonyl group. In addition, compound X shows positive tolerance and Felling's test. That means it is an aldehyde. Once if we know the structure of X, then we can try to write the structure of Y. Already we know that it has a methyl group which is bonded with a carbonyl group. We have to add the remaining 3 carbon atoms. This will be the Y. From these 2 compounds, now you can try to write the structure of olefin as this is the structure of alkene. Before going to the next problem, let us look at the mechanism of this transformation. Ozonolysis is an important transformation organic synthesis. When you have the alkene which can undergo one comma 3 cycle addition with ozone, to produce a cyclic intermediate. Which is not stable, which undergoes retro 1 comma 3 cycle addition to produce a mixture of carbonyl and carbonyl oxide This can undergo 1,3 cycle addition as this can be written you will be able to ozonide. Once you form this one, this depends upon the reaction conditions. You can convert it into carbonyl compound. In this reaction, when you use zinc, in water, it can reduce ozonide into aldehyde in this case. When you use zinc in water, zinc will be converted into zinc oxide and this will be reduced into aldehyde. In place of zinc, you can also use dimethyl sulfide, which will be oxidized to dimethyl sulfoxide, and you will be able to get aldehyde. You can also use hydrogen peroxide when it will be converted into formic acid by oxidative cleavage. So when you have the alkene which can undergo 1,3 cycle addition to give this intermediate which is not stable, this can undergo retro 1,3 cycle addition to give this carbonyl derivatives. Once we have this one, this can undergo further reaction to give the ozonide that can be converted into carbonyl compound using zinc in water or dimethyl sulfide or hydrogen peroxide to produce aldehyde, ketone and carboxylic acid. With respect to haloform test, whenever you have a methyl group which is bonded with a carbonyl group, this can be oxidized to carboxylic acid when you react with sodium hypohalite. It will be converted into haloform and carboxylic acid. With respect to tolerance and Felling's test, tolerance reagent can be made from aqueous silver nitrate, sodium hydroxide and ammonium hydroxide solution. When you mix all, and you will be able to form this complex. Once you have this one, when you react with the aldehyde, and it will be oxidized to carboxylic acid. For example, when you react with acetaldehyde, it will be oxidized to acetic acid, and silver 1 will be reduced to silver 0. So you have to use two equivalent of tolerance reagent. the silver one will be reduced to silver 0. This often we use to find out the presence of functional group in the molecule. This is we use for the determination of aldehyde functional group. Similarly, we can also use Felling's reagent. This is made from copper sulfate solution and sodium potassium salt of tartaric acid, and you will be able to form a copper 2 complex. When you react this copper 2 complex with aldehyde, it can oxidize to carboxylic acid. When copper 2 will be reduced to copper 1 as red brown precipitate. Here also you have to use 2 equivalent of copper 2 complex. It can be converted into copper 1 oxide. These are the common tests used to find out the aldehyde functional group. Now let us move to the next problem on increasing order of reactivity of the following sets of carbonyl compounds towards a nucleophile is. If you look at here, there are 2 sets of carbonyl compounds. First one involves benzaldehyde and substituted benzaldehydes. We have to find out the electrophilicity of the aldehyde functional group. If you look at here, you have the methyl group at the para position. Here you have the nitro group. As all of you know very well, methyl group can donate electron to the aromatic system. It can reduce the electrophilicity of the carbonyl group. On the other hand, nitro group is an electron withdrawing substituent. It can pull electron from the aldehyde group. Therefore, if you compare the electrophilicity of the carbonyl group of benzaldehyde, the electrophilicity of this aldehyde is reduced because due to the electron donating ability of the methyl group. Therefore, 1 will be more electrophilic comparing to 2. Now let us look at benzaldehyde and 4-nitrobenzaldehyde. This is more electrophilic because of the electron withdrawing nature of the nitro group. Therefore, this will be more electrophilic in nature. So this is the order of the electrophilicity of the aldehyde functional group in these molecules. So when you look at the reactivity of the nucleophile, as all of you know, nucleophile will be more reactive towards the more electrophilic in nature. Therefore, the order of the reactivity of nucleophiles toward this carbonyl compound will be same, and this aldehyde 3, since it is more electrophilic comparing these two, will be more reactive. Then benzaldehyde will be more reactive. The least reactive will be the 4-methyl benzaldehyde. This is the order of the reactivity of these aldehydes towards nucleophile. Now let us look at this aliphatic carbonyl compound. If you compare the electrophilicity of this carbonyl group with this one, and you have here hydrogen has been replaced with methyl group, which can give more electron density towards the carbonyl carbon. Therefore, the electrophilicity of this carbonyl carbon is reduced comparing to this carbon of aldehyde. Now, if you compare the electrophilicity of this carbonyl group with this one, and this methoxy group is can give more electron density compared to methyl group. Therefore, electrophilicity of this carbonyl group is further reduced compared to that. So, if you see the electrophilicity of the carbonyl group, it will be this order. Acetaldehyde, this carbonyl is more electrophilic comparing to this keto carbonyl group, which is more electrophilic comparing to this carbonyl group of the ester molecule. Therefore, the reactivity of the nucleophile towards this carbonyl compound will be as follows. Aldehyde will be more reactive comparing to the keto group, which is more reactive comparing to the ester group. Now let us move to the next problem. Hydrogenation of compound A having molecular formula C7H5OCl using K produces L, molecular formula C7H6O. Compound A with dimethyl cadmium gives M, that shows a positive haloform test. Identify A, K, L and M. If you look at compound A with dimethyl cadmium gives M, that shows a positive haloform test. That means it has a methyl group. That methyl group is bonded with a carbonyl group. From that, easily you can find out the structure of compound A as benzyl chloride. When you have a benzyl chloride, when you react with dimethyl cadmium, you will be able to form acetophenone. You need here 0.5 equivalent of dimethyl cadmium, and cadmium will which will be converted into cadmium chloride. Is mild reagent, it will not react further with this acetophenone. Now we can find out the structure of L as benzaldehyde. When you do hydrogenation using palladium in barium sulfate, it will be reduced into aldehyde. This is known as Rosenmund reduction. When you have the aryl or heteroaryl acid chloride, you can try to do hydrogenation using palladium, which is supported in barium sulfate. This is very crucial. Look at the reaction pathway. Palladium 0 undergoes oxidative addition with this acid chloride. This palladium 2 intermediate, which undergoes reaction with hydrogen, that undergoes reductive elimination to give aldehyde. To complete the catalyst cycle. If you look at here, it involves a partial reduction of acid chloride aldehyde. You have to try to remember the palladium should be supported on barium sulfate, then you can carry out the hydrogenation reaction to give the aldehyde as the product. Now let us look at the next example. Increasing order of the acidity of the following carboxylic acids is, there are two sets of carboxylic acids. First one involves benzoic acid and its derivatives. We look at these carboxylic acids as just we have seen the electrophilicity of aldehydes. Here benzoic acid has a methyl substituent, here it has a nitro substituent at fourth position. As we have seen earlier, the methyl group can give electron to the aromatic system. In other words, it can reduce the acidity of this carboxylic acid. On the other hand, nitro group can pull electron from the system due to electron withdrawing nature of the nitro group. Therefore, the acidity of this carboxylic acid will be higher compared to benzoic acid. If you compare the acidity of benzoic acid with this 4-methyl benzoic acid, this will be less acidic because the methyl group can give electron density to the carboxylic acid through aromatic ring. So the order of acidity of these carboxylic acids will be as follows. Three will be more acidic comparing to 1, which will be more acidic comparing to 2. Now let us look at the aliphatic carboxylic acid, fluoroacetic acid, chloroacetic acid and bromoacetic acid. And if you see the electron withdrawing nature of fluoro substituent is greater comparing to chloro substituent, which is more comparing to bromo substituent, therefore the acidity of the carboxylic acids will be in this order. The fluoroacetic acid will be more acidic comparing to chloroacetic acid, which will be more acidic comparing to bromoacetic acid due to the electron withdrawing nature of the halogen substituent. Now let us look at a series of reactions. The first one involves the reaction of toluene with chromyl chloride. We have to find out the intermediate. So when you react toluene with chromyl chloride and you will form this chromium complex, this when you do hydrolysis, it will be converted into aldehyde. This is known as Ettard reaction. So aldehyde can undergo reaction with amine. Here you have two kind of NH2, one is bonded with the carbonyl group, another one is with nitrogen. If you look at, this is more nucleophilic comparing to this NH2 because this is bonded with this carbonyl group. It can undergo addition followed by dehydration to give this compound. Chemoselectively, this more nucleophilic NH2 can undergo addition followed by dehydration to give this imine derivatives. And if you look at here, this involves ene reaction. This can undergo 2,3 sigmatographic rearrangement to give So it can undergo further reaction with another equivalent of chromyl chloride to give this chromium complex. Once we have this one, which can undergo hydrolysis to give aldehyde, this aldehyde can be further reacted with this amine to give these imine derivatives. Similarly, toluene also can be reacted with acetic anhydride in the presence of chromium trioxide to give benzylidene diacetate. This can be hydrolyzed to give benzaldehyde as the product. The next example involves chlorination of the benzyl CH bond. Chlorine in the presence of light can undergo homolytic cleavage to give chlorine radical, which can undergo reaction with benzyl CH bond to give benzyl chloride. When you reflex with the water, it can convert into aldehyde as the product. See, a substitution reaction, when you have the chlorine radical, it can react with the benzyl CH bond to give the benzyl radical, which can react with another chlorine radical to give the benzyl chloride. Similarly, this can further react with another radical. You will be able to form the benzyl chloride. Once you form this one, which when you react with water and reflux, and you will be able to form benzaldehyde as the product. Here, the transformation of benzene to acetophenone and benzaldehyde is given. This can be accomplished using carbon monoxide and hydrochloric acid in the presence of copper 1 chloride and anhydrous aluminum chloride. This is known as Gattermann-Koch reaction. In this reaction, the copper chloride helps to form formyl chloride. Carbon monoxide reacts with hydrochloric acid in the presence of copper 1 chloride to give the formyl chloride. Once you form this one, this can react with anhydrous aluminum chloride to give acyl carbocation, which acts as electrophile, which can undergo reaction with the aromatic ring through aromatic electrophilic substitution to give benzaldehyde as the product. Similarly, here you can try to react with acetyl chloride in the presence of anhydrous aluminum chloride, and you will be able to form acetophenone as a product. This is known as Friedel-Crafts reaction, Friedel-Crafts acylation reaction. Whenever you have the acid chloride, when you try to react with Lewis acid like anhydrous aluminum chloride, you will be able to form the acyl carbocation, which can undergo aromatic electrophilic substitution to give ketone as the product. The next example involves the transformation of nitrile to ketone and aldehyde. Nitrile can be converted to aldehyde by two-step process. When you react with tin chloride in the presence of HCl, you will be able to form imine intermediate. Tin chloride will be converted into tin tetrachloride. Once you form this one, this can be converted into aldehyde by hydrolysis. This is known as Stevens reaction. So whenever you have the nitrile, that can be reduced to imine. That imine can be hydrolyzed to aldehyde, which is known as Stevens reaction. In place of tin chloride, you can also use diisobutyl aluminum hydride. For example, when you react with the nitrile, you will be able to form the imine complex. This, when you do hydrolysis, you will be able to produce the aldehyde as the product. Either way, using tin chloride and HCl or dibol, you can try to reduce the nitrile to imine complex that can be further hydrolyzed to give aldehyde as a product. On the other hand, when you react with the Grignard reagent here, when you react with methyl magnesium bromide, it can undergo addition reaction with the nitrile group to produce this imine derivatives, which when you treat with water, it will be converted into ketone. So nitrile can be transformed to ketone by reacting with Grignard reagent followed by hydrolysis. On the other hand, you can reduce the nitrile to imine using dibol or tin chloride. That imine can be hydrolyzed to aldehyde. Now let us look at this example where you have the carboxylic acid as well as the ester group. If you look at this compound, it has a chiral center. The chiral center is intact. The carboxylic acid is selectively reduced. So this can be accomplished using diborane. When you use diborane, it can selectively reduce carboxylic acid without affecting the ester group. If we use other reducing agent like lithium aluminum nitrate, it can reduce both carboxylic acid and ester. Here, for a selective reduction of this carboxylic acid without affecting the ester group, you can use the diborane. This can reduce the carboxylic acid to alcohol. Once we have this one, this can be reacted intramolecularly with the ester group to give this lactone as a product. This is an example for the chemoselective reduction. Acid can be selectively reduced in the presence of ester using diborane as a reducing agent. Once you form this alcohol, which can be intramolecularly cyclized to give this lactone in the presence of acid under heating. The next example involves the reduction of ketone to alkane. The acetophenone is reduced into ethyl benzene, which has been further oxidized to benzoic acid. The benzoic acid also can be produced from bromobenzene. We have to find out the suitable reagents for these transformations. Ketone or carbonyl compound can be readily reduced into hydrocarbon by Clemmensen reduction using zinc amalgam in the presence of HCl that can reduce aldehyde and ketone into hydrocarbon, which is known as Clemmensen reduction. Alternatively, you can also reduce the ketone into hydrocarbon using Wolff-Fishner reduction, which involves reaction with hydrazine to give hydrazone. Once you form the hydrazone, this can be further reacted with potassium hydroxide, the ethylene glycol, at high temperature, which can convert into hydrocarbon. These two methods are used to convert ketone to hydrocarbon. Once we have this ethyl benzene, this can be oxidized to benzoic acid. This can be accomplished using potassium permanganate the presence of base. Whenever you have the benzylic CH bond, those alkyl benzenes can be converted into benzoic acid irrespective of the alkyl substituent. It can be methyl, ethyl, isopropyl. Once we have the benzylic CH bond, this can be converted into benzoic acid. The benzoic acid also can be produced from bromobenzene. It involves two-step reaction. First, you have to react with magnesium to give Grignard reagent. Once you form this one, you can try to react with carbon dioxide, which can undergo addition reaction to give the salt. When you treat with proton source, and you will be able to form benzoic acid, the product. Here the oxidation of alcohol to aldehyde and carboxylic acid is shown. Primary alcohol can be selectively oxidized to aldehyde using PCC. The structure of PCC is when you take 1:1 mixture of chromium trioxide, pyridine as HCl, they can form this salt, orange color salt, which is less reactive. It can selectively oxidize alcohol to aldehyde. This reaction can be carried out at room temperature in dichloromethane solvent. It doesn't oxidize aldehyde to carboxylic acid. On the other hand, when you take chromium trioxide in sulfuric acid, which is known as Jones reagent, it will oxidize the alcohol to aldehyde. The aldehyde will be further converted into carboxylic acid. This because chromium trioxide is more reactive comparing to the salt. Here the pyridine complex makes this chromium trioxide is less electrophilic, less reactive. It stops the aldehyde stage. On the other hand, when you take chromium trioxide and sulfuric acid, the aldehyde that is formed undergoes reaction to hemiacetal or acetal that further reacts with chromium trioxide to give carboxylic acid, the product. This reaction carried out in aqueous acetone. So depends upon the reagent, you can selectively oxidize primary alcohol to aldehyde or carboxylic acid. There are several methods are available. This one of the common method we use for the oxidation of alcohol to aldehyde and carboxylic acid. Here the reaction of aldehyde with concentrated sodium hydroxide is shown. Whenever you have the aldehyde, it doesn't have the alpha hydrogen atom. For example, this aldehyde has the alpha hydrogen atom. This can undergo aldol reaction. On the other hand, when the aldehyde doesn't have the alpha hydrogen atom like formaldehyde or benzaldehyde, these aldehydes, when you react with strong base like sodium hydroxide and potassium hydroxide, they can undergo self-oxidation and reduction to give a mixture of carboxylic acid and alcohol, which is known as Cannizzaro reaction. So in this case, you have the dialdehyde, which can undergo self-oxidation reduction to give a mixture of compound. The intramolecular reaction can produce this compound. In addition to that, there will be a intermolecular reaction between two different molecules, which can lead to the formation of if you look at the concentration of this compound, this will be higher since it is an intramolecular reaction, and this reaction can be further converted into useful compound. For example, when you reflex with acid, and you will be able to form lactone as the product. So when you look at the reaction pathway, for example, if you take benzaldehyde, when you react with concentrated sodium or potassium hydroxide, you will be able to form the addition compound, which can react with another aldehyde you will be able to form a mixture of aldehyde and alcohol as the product. So it undergoes self-oxidation and reduction to give a mixture of acid and alcohol. It happens when the aldehyde doesn't have the alpha hydrogen atom. If it has alpha hydrogen atom, the presence of acid or base, they can undergo aldol condensation to give alpha beta unsaturated carbonyl compound. Both aldehydes and ketones, they can undergo aldol condensation to give alpha beta unsaturated carbonyl compounds. Now let us look at this dicarboxylic acid with ammonia, which can undergo, whenever you have the aromatic carboxylic acid, they can undergo condensation to give amide. This amide, when you heat further, it can undergo further reaction to give imide as the product. This is an important compound. So when you have this dicarboxylic acid, which is known as phthalic acid, which when you react with 2 equivalent ammonia, you form the amide. When you heat it, it can undergo further reaction to give the imide as the product. Now let us look at these reactions. Here ester is converted to aldehyde selectively, reduced partial reduction. It doesn't undergo further reduction to alcohol. Here the ester is converted into tertiary alcohol. The partial reduction can be carried out using dibol. Just we have seen the reduction of nitrile using dibol. So diisobutyl aluminum hydride can undergo reaction to give this intermediate. This can be carried out in toluene solvent at negative temperature. This is very important. You have to use toluene as the solvent. So this intermediate, when you do workup, it will convert into aldehyde as a product. Ester can be reacted with Grignard reagent. Here when you react with the excess methyl magnesium bromide, two equivalent of methyl magnesium bromide, it can convert into tertiary alcohol. First, the Grignard reagent undergoes reaction to give ketone as the product. Once you form this one, this can undergo for another equivalent of methyl magnesium bromide to give the tertiary alcohol as the product. In summary, we have seen problems covering ozonolysis, Rosenmund, Steben, Clemmensen and Wolff-Fishner reductions. We also have seen problems related to Ettard, Caterman-Koch, Friedel-Crafts, Cannizzaro and Grignard reactions. We have seen the applications of Tollens, Fellings and Jones reagents. We also have seen one example for the chemoselective reduction of carboxylic acid in the presence of ester using diborane. We have seen two sets of compounds to determine the acidity of the carboxylic acids, aromatic as well as aliphatic carboxylic acids. In case of aromatic carboxylic acids, the substituent, the aromatic ring, determine the acidity of the carboxylic acids. When you have the electron donating group, it can reduce the acidity of the carboxylic acid. On the other hand, when you have the electron withdrawing group, it can enhance the acidity of the carboxylic acid. Similarly, when you go for the aliphatic carboxylic acid, the electron withdrawing nature of the substituent is crucial. If you have the electron withdrawing substituent, it can enhance the acidity of the carboxylic acid. Similarly, it can also affect the electrophilicity of the carbonyl group. We have seen two sets of compounds towards reaction with nucleophiles. I hope this lecture will be useful to you. With this, we conclude. Thank you very much.